Okay, there we go. So this is our last time that we'll be meeting this way, hopefully the last time. So on Monday, we'll be face-to-face, and that'll be, I think, that'll be good for everyone. I'll be able to see you, you'll be able to interact with me. It'll just, I think, overall be wonderful. We'll also start labs next week. Say more about that when next week comes. I will start grading your the last daily homework you did. I'll probably start grading that today. Get that to you, and then there will be another one up that'll be there'll be some sketches, like the qualitative sketches we're doing here. I'll have you do some of those for Monday, and then we can start doing a lot more stuff after we get kind of that preliminary stuff taken care of. So we're going to be meeting on Monday, and it's going to be in room 230. That'll easily hold the class, no problem at all. So 230 is in the Science Center. It's on the second floor, and it's actually right across from where my office is too. So you also get to see where my office is. Again, anytime if you want to just meet with me to discuss something, if it's not during an office, send me an email, and I'll set up a Zoom meeting with you. Starting next week, you can actually stop by my office, but you can always at any point, we can still meet via Zoom if you feel more comfortable that way. You can just send me an email, and I'll send you a link, and we'll go from there. Okay, so we're doing these qualitative V versus T graphs. And this is a really good skill to have. This type of reasoning comes up a lot in physics. And so really kind of master it. We're going to see a variation on it again today. So what did we end up doing? We had this position versus time. So we said this might be a car. Maybe this car is driving this way here. And we said we want to find the actual velocity at this point here. So find the velocity here. Find the actual velocity here. In other words, at this point. We said another word for the actual velocity is instantaneous velocity. So we could just as well say the instantaneous velocity. And since instantaneous velocity is kind of a pain to say, we're just going to start calling it the velocity. So we'll just start saying the velocity. So if I say find the velocity at this point, or instantaneous velocity, or actual velocity, they're all the same thing. So what was the reasoning we had? We came up with an approximation first. So what was the approximation we had on Wednesday? We said, I have no idea what the velocity is here. I'll give you an estimate. What did we say the estimate is?
It's the limit as t approaches 0, or delta t approaches 0.
That's going to be the exact result. So hold on to that. So what was actually the approximate thing? Then we're going to get to what you said.
Just get like two t's that are just like right next to the point, find the average.
Yeah, so what we did is we said, okay, well, and this happens all the time in physics. If you can't answer the question you want, you ask a question, you try to answer a question kind of similar to it. See how well it works. So I said, I have no idea what to do. Well, I'm going to take this point here T1. I'm going to call this point here T2 for no good reason. And I know at this point, the car is at some position X1. At this point over here, the car is at position X2. And what I can do is I can then define the average velocity, because I know the average velocity. The average velocity is by definition, it's the change in distance over the change in time. So if I were to draw this here, this value minus this value, this is my delta t. And this value minus this value is my delta x, and so here's my delta x. So I can take delta x over delta t, and we said, hey, that's the slope of that line connecting these two here. So we could say that the velocity here at this point, the velocity at t, is approximately the average velocity between t1 and t2. But we can take this crude approximation and make it better and better and better. And what did we say we do in that case?
Bring both t's closer.
Yeah. we take these, we make it smaller and smaller and smaller and smaller. So if you make it even smaller, if I go here and here, so here's my new, so here's my new T1 and here's my new T2, like this. So this right here, that separation distance here, that's my new delta T, and this distance right here, that's my new delta X. But then take the slope of this line right here, delta X over delta T, that's a better approximation. So a better approximation occurs, so a better approximation occurs if we move T1 and T2 closer to T. Does that make sense? And so what do we do if we want to get a better and better and better approximation? We make this smaller and smaller and smaller and smaller. It can never equal 0. There's actually somebody else sitting in on this class, or lab tech, because he may have to start doing things more for the class. He's not here right now, but he was. I think it was Robert, I think you asked a question about why don't you let it equal 0? And he says, and I mentioned, you said why don't you let it equal T or something to that effect. I think you meant the idea, why doesn't the delta T equal 0? And I think Kevin said, I think Robert probably meant the following. So I'm going to try to re-answer your question just in case you did ask that question. So what we could do is we could say the actual velocity at this point. So what did we say then the actual velocity at this point is? Mathematically, how do we write this? What do we say? I think, Julie, you already said it. What was it?
The limit as delta T approaches 0 of the delta X over delta T.
Yeah, so we're going to take the limit as delta T goes to 0, this delta X over delta T. Meaning you can get the exact same picture, but these 2 points are right on top of T. They're not on top of each other, but they're really, really close. So it's almost really hard to imagine. So this guy here is going to be right here, and then this fellow here is going to be right there. There's almost no width there. So there will almost be no width in the vertical direction there either. And this is going to be then the fundamental definition of the actual velocity. And we said this is really this is actually the formal definition of what it means to be a derivative. And so if you wanted to write this in terms of calculus notation, which we're not going, you don't need calculus for this course, but conceptually calculus is trivial. What this is dx dt. So this is writing it in terms of what's referred to as differential notation. That d here, it's just like delta, but a d, when you have a d instead of a delta, the d just means something that's extremely small, so it's called an infinitesimal. So this d here, this dt here is almost exactly 0, not quite. It has to be, it can't be quite 0, but it gets really, really close to 0. And this dx is really, really close to 0. So in other words, if you had a car flying down here like that, if I wanted the velocity right here, what's going to happen? That car is going to move some tiny little distance, call it dx, or basically a delta x as it becomes really, really small. And how long did it take to move that tiny little distance? Well, that delta t when it's really small, what we call in calculus dt. So it's basically a distance over time. Does that make sense? And conceptually, that makes perfect sense. Because if you think about velocity, what does velocity mean? Velocity is basically how fast does it take to travel from here to there. So you need to know how far you're going here, and then how long it takes to get from here to there. And that ratio there is what you mean by velocity. So does that make sense conceptually? Now let me go back and say, so why can't, you could say, again, the person sitting in here said, I think Robert really meant, why can't you let delta t equal 0? So I don't know if you meant this or not, but let's say you did. So why can't delta t equal 0? Why does it have to approach 0? It can never be 0, but it can get really, really close to it. Why can't it equal 0? And think about what it means to be velocity. It's got to some point. Okay. By velocity, you actually have to travel this point and this point. So at this point, you're at some fixed time. At this point, you're at some fixed time. And the time it takes to go from here to there is what we're calling delta t. If that delta t is 0, what happens? It means that t1 and t2 are at the same point. If t1 and t2 are at the same point, how far have you traveled? You haven't traveled any distance, right? Because you're at the same point. The t1 and t2 are at that point. If you're at that same point, you can't travel any distance. So it doesn't even make sense to talk about velocity. You have to have a small difference in time. You have to have a t1 here and a t2 here, which might be really, really close together, but they can't be exactly the same. That's why you have to do this limit thing. Does that make sense? It's a pretty technical question. So again, what you want to understand here is just kind of get the conceptual idea here, is that you're just taking a change in distance over a change in time, but that change is going to be really small. The car is going to go like that, so you're going to measure it when it's here, and then you're going to measure it when it's here. So there's going to be some tiny little distance. Calculus-wise, we call it dx. The time it takes to go from here to there, we call it dt. Now, conception, so does that part make sense? Questions? Now, graphically, what do we say this is? Graphically, this is so graphically, what is that quantity here? Either written like this or like this. The actual velocity at this point here is nothing but the
derivative.
Okay, we call it the derivative, but what is it conceptually? Picture-wise.
Oh, the secant.
Okay, well, it's really, really
line.
small. So that secant becomes the
Tangent line.
tangent at that point. So this graphically is the tangent, is the slope of the tangent line. At t. So if I were to draw another little cartoon picture to help you see this. This is why calculus is actually easier than almost any of the other math courses you can take, because calculus is very visual. And I think when you can start visualizing math is actually a lot easier to deal with. So what you have here, here's our curve. Initially, we had this point here. And that's the slope of our secant. Then we made it smaller. It's still the slope of the secant. Then we made it smaller and it gets harder to draw. Like that. Then eventually we make it even smaller, so we get the slope, this slope right here. Well, that's going to be the slope. Oh, that's kind of sad. The slope of a line that touches at one point. So this right here, this is the slope. This is the tangent line. And the slope of this is the velocity of the object. So when you draw these v versus t graphs, what you're really doing is you're making a graph of the slope at all the very different points here along here. That's all you're doing. So let's take an example. We did one last time. We're going to do it again. And we started it. We had a kind of a sine curve thingy. So last time we had a curve like this. And we said one way we're going to get this is actually, the fancy name for it is called a simple harmonic oscillator. It just means you have a mass on a spring. So we're going to have a mass on a spring, we're going to go like this, we're going to assume there's no friction, and this is just going to go back and forth like that. And again, it turns out that's really the only problem physicists really understand. And that turns out to be fine, because it turns out many, many, many things in the universe reduce to that dumb little problem. Okay, so I want the actual velocity at any given point on this graph here. And so what do we do here? We have to basically, this velocity here, this is going to be a graph of the slope of the tangent line. The tangent lines on the x versus y graph. So I told you there's kind of a nice way to do this. So the first thing when you have when you go to make this graph here, always go for the easy points. And what did I tell you were the easy points?
Maximum and minimums?
Yeah, this max here and this minimum here. Again, so if you're at a maximum here, if you draw a slope, you get 0 there. If you're at this minimum, draw the tangent line, again, you get a 0 slope there. And again, let's conceptually make certain it makes sense why the object's 0. Again, what does velocity mean? You move some distance and some time. So let's look here. So if I'm at that top, I'm initially here, then I'm 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 here. How much has the distance changed here? It hasn't. That's why there's no velocity at that point. Let's go down here. I'm here, and then I'm here, and then I'm here, then I'm here, then here, then here, then here. How much has that position changed? Well, it hasn't, which is why there's no velocity here. So at this time here, at that time here, the slope is 0. So I go down to that same time here. When you do this, draw an actual dotted line here representing this point going all the way down to here. This is the time. And that's where you need the 0 bit right there. I'm going to do the same thing here at this time here. So at that time here, there's no slope. So I go extend this down here and I go with this. So get those zeros in the graph first. If you don't get those zeros, you can start getting some funky stuff. Again, make physics easy on yourself. Now what do? You start on this side here and you just march along here and look at slopes. Okay, so let's stop here. Does this part make sense? Questions? Okay, let's look at slopes. So we start here. So I draw my little slope here. And here's my first slope. What kind of slope is that? If you have a line like this, that is?
Positive.
Positive. So at this time t equals 0, I draw some positive slope. Now I'm going to go here. What kind of slope do I have here?
Positive, but less positive, or like smaller,
Yeah.
not as steep.
It's going to be less positive. So at the same time here, right? This is still positive, but at that same time here, I need something that isn't as big as this guy here, but still positive. So that goes here. Now let's go over here. What is that slope?
Negative?
Negative. I go down to this point here. I draw some negative value. Now let's go here. What is that one? Right, that's my slope. It's like that. So what is that guy?
Super negative.
Oh, it's going to be more negative. Okay, is that something like this is going to be, really, really negative, if it's like that. It's going to be like that. So we're going to come down here and we're going to have something maybe like this. Now what about something right here?
Less negative.
Yeah, less negative, so we do the same thing here. So I have something like that. And then we just keep on marching along. Then we go to 0. If you go here, we get something slightly positive. So I have something slightly positive. If I go here, it's more positive. So I have something like that. Then you connect the dots. Now, okay, this is something I'm just going to qualitatively, this makes sense. If this is a nice, smooth, continuous curve, this curve here is going to be nice and smooth and continuous. It's not going to be jaggedy. So try to make something that looks nice and smooth. And so, okay, just out of curiosity, for those of you who have had calculus, if you do, what should this curve end up being? If you don't know this, don't worry about it. This will end up
Curve?
good. This ends up being a cosine curve. So I'm going to draw, I'm going to kind of connect these guys here like this. Let me move that up here. If you do this actually, if you were to do this rigorously mathematically, in other words, if you take a course in calculus, what you'd find out is that if you actually do this expression exactly, you end up with a cosine curve. Mine, since I'm doing it kind of qualitative, is for a cosine curve, but it's more or less cosine. Does that make sense? Questions? So this idea of graphing the slope, we're gonna come across that quite a bit. Questions?
So the V versus T graph, it's more like a cosine curve. It's not like straight lines.
Correct. So no, okay, now my qualitative graph, you can't tell that because it's, you know, I'm doing it qualitative. So somebody might say, well, is it kind of like straight line? Well, qualitatively, that would be more or less the same. I mean, but if you were to actually go through and have a math for this, and you don't need calculus for this course, what would happen here is actually you get a perfect cosine curve. Now, if you were to draw something here that looks kind of cosine-y, but not quite, qualitatively, it's the same thing as far as I'm concerned. Okay? Questions? Let's try another one. So here's some x versus t graph. I'm going to actually put some numbers here. I'll make this, let's say this is 2. Let's say this is 8. Let's say this is 5. That scales something awful. And we will say that this is, okay. I want you to make the v versus t graph for this. This is a straight line, and this is some curvy thing. What would you do? Again, I want a qualitative one here, although we're going to be able to get a couple numbers here.
Put zeros at 2 and 8.
Put zeros at 2 and 8. How come?
They're the maximums, but there's also that like horizontal line between them.
Okay, connect the ideas together. Okay, so what is it? This is the slope of, this is a graph of the slope. So if I'm right here, or here, or here, or here, or here, or here, what's the slope at any of these points here?
0.
Exactly, right? The slope here is 0, 0, 0, 0, 0. So between 2 and 8 here, what has to be the velocity? 0. Okay, tell me why you didn't need calculus for this. What does velocity mean? It means the object's moving. Between 2 and 8 seconds here, what is this object doing?
Not moving.
Yeah, it's staying at 5. So if you have an object staying in the same position over a period of time, that's called not moving. Crazy, right? And that's what this is why it has to be 0. Okay, let's go from 0 to 2. Again, this is a straight line section. So what do I know about this slope, and this slope, and this slope, and this slope, and this slope?
It's the same.
It's the same because it's a straight line, right? So if I draw the slope here, it's like this. If I draw the tangent line here, it's like that. Tangent line here, it's like that. Here, it's like this. Anywhere along here, the slope is the same. So if the slope is the same between 0 and 1, what would I draw down here?
A straight line.
It's a straight line like that. Right? Because this slope is the same as this slope, is the same as that slope, is the same as that slope. Hey, in this region here, I even know what the numerical value of this has to be. What has to be the numerical value there?
Whatever the slope of that line is on x versus t graph.
You tell me, what is the slope on that graph? What is the definition of a slope of a straight line?
Change, or well, in this case, it'd be delta x over delta t.
Okay. And what would you, when you first learned this in algebra, what does your teacher tell you? Slope is?
Rise over run.
Rise over run. What is the rise? What is the run? This is your rise, which is 5. What's your run? From 0 to 2, your run is 2. Right? So the slope here, in this case, because it's, you can only do this because it's a straight line. It's just rise over run. So this has to be 5 over 2. So this is actually 5 halves. We have units here, so 5 halves meters per second. That's the crappiest 5 I've ever seen. Does that make sense? Now, we're not as lucky here because we don't know what the mathematical form is here, so we can't come up with any numbers here. So this right here is going to be qualitative. Okay. So let's figure this out. Suppose I'm right here compared to right here compared to right there. How does the slope at this point, and this point, and this point look? The slope here is
Negative.
a little bit negative. So I come down here at this point. I have some dot here for something a little bit negative. How about the slope right here?
More negative.
More negative. And so I come down here to that point here, I'd have something like that, and then even more negative down here like that. So I'd have something like that. Okay? So qualitatively, this is what this graph would look like. Does that make sense?
Would you connect the horizontal on the V versus T graph? Would you connect the
Here?
would you connect that?
You could, but I wouldn't. If you want to have like a dotted line, that's fine. Mathematically, this is called a true discontinuity. So in other words, the actual value here, are different. And so normally you wouldn't draw a solid line there. But if you did, in this course here, I wouldn't be fussy about it. But normally you wouldn't connect those. So in other words, if you gave me this, as long as that was a straight line here, that would be fine. I probably wouldn't do it. I'd either make it dotted here, or I'd take out the whole line itself. Either would be acceptable. Any of those cases would be acceptable here. Discontinuities rarely occur in physics. They do occur. But usually when you get a discontinuity in physics, you're getting something really, really quite odd happening. Questions? Okay, let's extend these ideas. Again, remember we're looking at kinematics. We said kinematics is the study of motion. So we want to know basically what the position is a function of time, something like this. We also want to know the velocity of an object, how it's moving, something like this. And the next term we need is something called acceleration. And once we get that, we can start doing a lot more. So we're going to extend these ideas to acceleration. And it's going to look a lot like what we already did. And this is kind of one of the lessons in physics is in physics, once you understand something, you learn a trick, you can beat that trick to death because you can get a lot of mileage out of it. So we're going to talk about acceleration. We're going to talk about acceleration. First of all, we have to define it. So let's go back to our exact replica of a Honda element, which looks exactly down to the perfectly scaled like this. So this is at some time t1. This is at some position x1. Again, here's our origin. And let's say the car here has an actual velocity of v1. So that's how fast we're moving here. When the car drives down the road, now the car comes over to here. So now let's say it's down here. And so this is at some distance x2, and at some time t2. But now the car has a different speed, has a different velocity. So this right here I'm going to call v2. Maybe it's more, maybe it's, I'll make it a bigger arrow here like that. That's v2. So we defined something called the average acceleration. And this is, okay, I'm going to put the bar on it for average. And the 3 lines here means this is a definition. So does anyone know what we define the average acceleration to be? Maybe you had this in high school, or maybe you kind of intuitively know what it is. Not one bit obvious unless you've studied that.
Would it be delta V over delta T?
That sounds like a great answer. That's what it's going to be. So acceleration is going to tell us how the velocity changes. So what we're going to do is we're going to take the V2 here, minus the V1 here. And as Julie said, again, when you have a final minus initial, that's always a change. So this will be the change in velocity. But we want to know how long it takes that velocity to actually change. So we divide it by basically when it has a velocity here. So at time t2, it has that velocity v2. And here, at time t1, it has velocity v1. Okay, so this is how long it takes the velocity to go from here to there, t2 minus t1. So we divide it here. So the average velocity is just a change in the velocity of the object over how long it takes to change. Does that make sense? We need units for this. Okay, we're going to do MKS. What's another name for MKS?
SI.
SI. Okay, so again, we always use brackets for, or I always use brackets for units. What are the units for velocity, right? This is a change in velocity, so it has to have the same units as velocity. So what are the units for velocity in MKS?
Meters per second?
Yeah, this has to be meters per second. Then we have to divide this by change in time, so this has to be seconds again. And so the units for acceleration are meters per second per second. Okay, that looks awful, okay?
So can it be meters per second squared?
That's exactly how we're gonna write it. Because this right here, it's not wrong, but it's no one ever writes it like this. And so what happens if you take meters per second divided by seconds, that's the same thing as saying meters per second squared. Okay? What would we have in CGS?
V over second squared?
I'm
Or
sorry.
CGS? Oh, never mind.
So what is this? Velocity in CGS units is?
Centimeters over seconds?
Squared, exactly. So this would be centimeters per second. That would be the velocity over seconds. And so this would be centimeters per second squared. Okay, let's finish it up with English. Okay, what would be our velocity in English? Feet per second. So we'd have feet per second. And so this would be feet per second squared. Okay? Again, we're almost always use this one here. There'll be one thing where I'll use this here when we get to it, I'll explain it. Because you actually hear it used periodically. Okay? So that's our definition of average acceleration. Hey, let's figure out what it is graphically. So graphically, what is average acceleration? Okay, let's make a graph of this. So now I'm going to graph the velocity versus time. You're going to see something like, hey, we just did this. And that answer will be yes, yes, we did. So maybe this is the velocity of your car driving to Hornell as a function of time. And let's say your velocity driving to Hornell as a function of time looks like that. I'm just making something up. So here's T1. And at T1, you have a velocity here, V1. At T2 here, you have a velocity here, V2. So graphically, tell me, and I erased it. Tell me what this is. Where's delta V and where's delta T on that graph? And so graphically, what does this represent?
Average acceleration.
It is the average acceleration, but what is it graphically, in other words, in that graph?
Slope of the secant line.
That sounds like a great thing. That's exactly what it is. So this right here, this right here is my change in time. Well, this right here is my change in velocity. So here's my change in velocity. So if I take delta V over delta T, that's going to be the slope of the secant line. So this right here, this is the slope of the secant line. And the V versus T graph. Does that make sense? So that's what the average velocity would mean, average acceleration. So again, average acceleration means if something is accelerating, it means that the velocity is changing. Maybe it's changing in the positive direction, maybe it's changing in the negative direction, but the main thing is that the velocity is changing. Questions of that? Okay. What do you think you're going to want? This is the average acceleration here. But I might want to know, suppose we're right here at some time right here. I want to know what the actual acceleration of the car is here. Hey, I wonder how we're going to do that. So let's ask, how would you find the actual acceleration of the object at time t? So I'm right here, and I want to know how is the car accelerating right at this point right here. In other words, if this is your velocity as a function of time, at this point right here, you have your foot on the accelerator. Your car is going faster. You know, so what is your acceleration right at that point? Hey, what are we going to do? It's going to be as dumb as you think it is.
Which would be the limit.
Okay, keep going.
The limit of, as t approaches 0, of dv over dt.
Or delta
Or
V.
delta v over delta t, I should say.
Yeah, that's exactly what we do. We do the exact same thing we did with the velocity. So to kind of set it up again, you could say, really, we get the point, but as an important enough point, I want to just really kind of, beat a dead horse. Don't know why my horse is dead, but that's not the point. Okay, so let's figure out why. Actually, I like horses. Turns out I'm allergic to them. Oh well. But that's not really relevant to this class. So if I want to find the actual acceleration at this point here, what I can say is that it's going to be approximately the average acceleration between T1 and T2. So I can say I have no clue what the acceleration is here, but I can say the acceleration is going to be about the average acceleration between these 2 points. And we show that to our friend, and we're proud that we came up with this. And our friend says, oh, we can do better. I can make this T1 and T2 closer. I can make them here and here. That's my new V1. And that's my new V2. And I can say, oh, that's a better approximation. then another friend can come along and say, oh, well, I'm going to take my new T1 to be here, my new T2 to be here, and then that'll be a better approximation. So again, how can I get a better and better approximation? I do the exact same thing. I'm going to say the actual acceleration is the limit as this delta t goes to 0 of this change in velocity over the change in time. Does that make sense? It's the exact same thought process that we used in the velocity case. And that's one of the nice things about physics is you take an idea and you just really kind of beat the thing to death. You really get a lot of knowledge out of one good idea. And again, this makes conceptual sense. What does it mean for the object to accelerate? Acceleration always means the velocity is changing. So what does this mean here? The object is going boom like that. So when the object's here, it has some velocity this way. When the object moves over to here, it has another velocity this way. I take the difference there in the velocities. That's my change in velocity. And how long did it take to go from here to there? Well, sometime delta t. So if I want a better and better approximation of the velocity, the acceleration here, what I have to do is I have to measure the object here and here some tiny little time apart from each other. And that's what I do conceptually. Now, mathematically, how would you write this? And so, again, you're not in calculus. But if you're in a calculus course, how would you write this quantity here?
dv over dt?
Yeah, you just say dv over dt. Again, that's the differential way of writing it. And again, in calculus, a d, it's just like a delta, but it's just exceptionally small. It's extremely small. It's called, the mathematical word for it is called an infinitesimal, meaning it's so small. It's not quite 0, but it's infinitesimally close to 0. So you take an ever so slight change in the velocity over how long it takes to do that ever so slight change. And that ratio right there is your actual acceleration at that point. Does that make sense? Hey, graphically, what is this? Graphically, this is what is that?
Slope of the tangent line.
Of the v versus t graph, right? So this is the slope of the tangent line of the v versus t graph. So if you had a v versus t graph, and if I wanted an a versus t of that graph, you do the exact same thing we did for position versus time to get the velocity versus time. There's no variation in this. So let's do one. Let's say I have this. So let's say I have an object like this. Want the acceleration versus time. First of all, tell me what, if you had a picture like this, tell me what that means about describe an object that moves like this. Let's make certain we understand that. So let's say you're going to Wegmans and you go down the velocity versus time graph and you happen to bring this home. Okay, what kind of object are you bringing home? Describe it to me. Let's start off with the car right here. If this is a graph of my car, what is my car doing?
Slowing down, or going forward, but slowing down, and then once it crosses the t-axis, put it into reverse, speeds up at the, I kind of lost it.
Well, actually, you're doing pretty well. You just kind of stopped, but you're doing actually pretty well. Okay, so what happens here? This right here, this is positive. What does it mean to have a positive velocity?
Going forward.
Yeah, if you're going this way, it means you're going to the right. So this means it's going to the right. If we're talking about up and down motion, what would that be? It'd be up, okay? So what happens, the object has some velocity going this way. So I'll give you some points. So this would be point A. I shouldn't call that A. This would be 1, 2, 3, 4, 5. So this is the object here initially. This is point 1. It's moving that way. As it's moving to the right, what does it do? What does the velocity do? You can see it's less and less positive. So it means it slows up. What's happening at point 2? At point 2, it is?
Stops.
It stopped because the velocity is 0. So it slows up, slows up, slows up, stops. So this is v equals 0. This is point 2. Then what does it do? From here to there, this is a negative. What does it mean to be negative? It's going to the left. If you're doing vertical motion, it means it's going to the it's going down. So what happens here? Well, this goes negative, more negative, more negative, more negative, the most negative here. So what does that mean? If it's negative, more negative, more negative, most negative, what does that mean? The object's speeding up, going to the left. So the object starts here, slows up, slows up, slows up, slows up, stops momentarily, and then starts speeding up going this way. So let's say this is going to be, this will be our car this way. Now it's going faster this way, so this is at 3 here. Now what happens to the object? What happens between 3 and 4?
They are same going to the left way, but stop at 4.
Yeah. So what happens here? It's still going to the left, so it's still moving this way. But what's happening is going less and less fast to the left. And eventually at 4, it's stopping. So it slows up, slows up, slows up, slows up, stops. So this would be point 4, this is stopped. Okay, then what happens? What happens from 4 to 5?
Start moving to the right again.
So it's going to the right and speeding up because it's going faster, and you can see that the velocity increases. So it goes fast, it starts going to the right faster and faster and faster and faster. So maybe it ends up over here. So maybe, who knows where it ends up? This is only the velocity, you don't know about the position. So you get that. So that's what something like that would describe. So don't get lost into what these graphs mean. Kind of always think about an object moving that way to see if you kind of understand it. So the question is, what is its velocity versus acceleration versus time? We'll finish this up and we'll call it good for the day. Okay, so this acceleration, so is there questions about what this object means? About this graph means? Okay, so the acceleration here, this is going to be the graph, this is going to be the slope of the v versus t lines. So how am I going to graph this? So this picture is kind of cluttered. I'm going to redraw it over here. You don't have to do this. I'm just doing it because that has too much crap on it. Okay. So what did I do? Told you to do to graph the slope. What's the first thing you always do with these things?
Find the maximum and the small, that minimum.
Yeah, so you always graph your maximums and minimums first. If they have any, it may not, because they're going to be the zeros that you're incorrect. So here's a minimum. I draw my little slope. That slope here is flat, so that means it has no slope. So that means at that time here, the acceleration of the object is 0. Again, what does that mean here? Well, if you look at the velocity, if you look at the velocity here and 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 here, the velocity is not changing. But the velocity is not changing. That's what it means if the object is not accelerating. Okay, what's the next step? You start on this end and you work to this end just drawing slopes. So you're going to start here. I'm going to draw a slope. What kind of slope is that?
Negative.
Negative. So I'm going to put it here. So at time t equals 0, this is a negative slope, so I put it here. Now what happens if I go about here? What's the slope here? Still negative, but not as negative. So I'm going to go at this time here, and have some less negative value there. Now what about right here? What's that?
Negative.
Right
Wait,
here.
no, that's a positive.
Yep, slightly positive. Okay, so that's slightly positive. So I come down here at that point and have something slightly positive. I go over to here, more positive. So I have that, and I get something that goes like that. That's what that would look like. Does that make sense? Questions with that? So it's the exact same thought process that we did to produce a V versus T graph given the X versus T graph. Questions? Okay, so we'll do another example of these starting on Monday in person. And then we're going to do something, which pretty much we're going to do for the rest of the semester and all into next semester as well. We're going to take a special case. So this is a little preview. We're going to specialize to the case when the acceleration is a constant. We're going to say, suppose the acceleration of our object is a constant. Can I determine anything about the velocity versus time and the position versus time? And it turns out you can determine a lot about them. You're going to get mathematical expressions, nothing really complicated, to actually describe them. But it turns out that whenever you have constant acceleration, and it turns out you have constant acceleration all the time, you can use those expressions. And so the mileage you're going to get from those equations are going to be phenomenal. Okay, questions with this? Okay, so I'll make a homework assignment that we do Monday, and I'm just going to give you some X versus T graphs and some V versus T graphs, and I want you to calculate qualitatively the V versus T and the A versus T graphs. So you can just get some experience with this. Questions? Have a great weekend. Don't worry about your Wi-Fi lagging, that's fine.